Hello, it is me, Ugo. So this is a practice, revise, reflect on communicating skills. So this is basically the umpire thing. This is a video for it for the last non-zero digit of factorial. Um, yeah. So the factorial problems, or at least the one before, used a mathematical um solution. So it was basically taking advantage of math principles and like calculus to solve for the leftmost number in a factorial, which took it down from the O of n log n time to O of 1. Uh, and I mean, that's crazy. It also prevented overflow, integer overflow, whatever it's called. Is that what it's called? I think so. I forgot. Sorry, I'm a little sleepy. Yeah. Integer overflow. So that was the previous problem, but this one is asking for the rightmost one. The initial, or actually, let's go back over here and try to understand the problem. So first, we're given an integer number called n, or at least I called it n, because it says n in the problem. And it's just an integer. And what we're supposed to do is we're supposed to find the last non-zero digit of the factorial of the input. So we're going to find the factorial of the input, and then we're going to get the last non-zero digit. The problem is factorials grow really quickly. So you have problems with integer overflow. You have problems where there's going to be a lot of trailing zeros. And this causes the time and the amount of steps taken to solve this problem to grow quickly. It's crazy. So a more optimized solution is needed. And we're just supposed to output the trailing number. So, I mean, if we look at like 5 factorial, it's 120. So the solution we'd be looking for is 2. And I think it shows right here. Okay, yeah. Sorry. So to the one thing that we have to worry about is the constraint. And I put a calculator on it because it just makes it nice, and that's going to be the input test for all of them in Python Tutor. Because there's 4 solutions that I've seen so far. 2 of them were the ones I came up with. One of them is the simple one, and one is the more optimized one. Geeks for Geeks, I think, had a more optimized solution than mine, but then their other solution also failed. So, or at least wasn't efficient enough to run in Python Tutor. So yeah. Yeah. So the constraint is that n can be between, or includes. I don't know. I don't know how to describe it. It's in the range of 0 to 530. This might seem like a small range, but for factorial of 530 is an insanely large number. There's no way that isn't causing integer overflow if you just try to store that in an integer. So, or maybe Python. I think Python gives like 64 bits for one, so maybe, I don't know. So I looked at this one for a little bit, and then I looked at this, and I was like, okay, this is a little weird. I don't quite understand it. So I went to their little link over here that said an explanation for it. I still didn't really understand it. So I searched up a video, and then this video helped me understand it. I liked this one, but this one's a different solution than what Geeks for Geeks had. But basically, essentially what's happening here is we have 2 to the a times a factorial times b factorial. And this isn't really a good writing of it. Basically, we're just getting the last non-zero integer or digit of each of these 3 things. So because of that, we're going to only be multiplying single digits together, which means it keeps it very small. And a is going to be an integer division of 5, while b, unfortunately they didn't write the modulo sign, but b is supposed to be the modulo or the remainder of n modulo 5. So So I think later on he writes, yeah. So he writes a quotient and remainder. So this is the remainder of 5, and this is the quotient of 5, and the quotient of n divided by 5 is going to be the exponent of 2 that gets multiplied to this. And the last digit of all three of these will be multiplied together to give us the last non-zero digit of n factorial. So when trying to code this, or let me explain why we do this. We do this because after the fifth factorial, I think it was here that he explained it. After the fifth factorial, we start getting a leading zero because 5 factorial will have the product of 5 and 2 inside of it. And because of that, we can guarantee that anything before it will have a number in the ones place automatically. But after that, we will have to worry about the leading zero, and that increases the number that the integer could be. So to avoid integer overflow, we can do this instead. So from here, I decided to look at how he did it, or the examples of them, to understand a little better how it worked, because his writing kind of left out a lot of details. But basically what I just explained now is exactly what he's doing. And I didn't realize it, but you can do it. This could be, or this is supposed to be recursively done. I didn't realize it until this step where we had 20, or because of 103, and 20 factorial would be so big that it could actually go back into the function, or should go back into the function, so then we could calculate it more easily, because in the other ones he kind of just did it by his head, or in his head. But then right here he showed that he actually did it like recursively, where he got this and passed it into the function again, where he used 20 as the n and then used that to get another smaller solution. So with that information, I went back over here and I started trying to code everything. Yeah, so in here we have the base case. This is the base case because we're going to be using recursion. So to stop the recursion, we're gonna stop it when n is less than 2. Yeah, we're gonna stop it when n is less than 2. I'm pretty sure I could improve the efficiency of the base case, but I didn't want to risk it because recursion's a little tricky for me sometimes. Like I'll mess things up. So just to keep it simple for now, just this is the base case. So eventually we'll get the recursion down to this, or to a small number that's less than 2, where we'll return 1, and that'll get us back up the call stack. We have a function inside of the function. I didn't know that you could do this in Python until I searched it up. And I mean it kind of makes sense to have this, because it's like it encapsulates the logic into the actual function you're supposed to use it for, rather than letting it be a thing outside of it. So I like that part of it. I put it after the base case because it's like, okay, we don't need to define the function if the base case is triggered immediately or something like that. So this is first, and then after that we do the actual code for the function. It's not too long, I think. So in the function, I think they were called inner functions, we take in an exponent, and this is because the power of 2, exponent of 2. Was it exponent of 2? Yeah. So the exponent of 2 has a last number cycle that repeats. So it goes from 4 to 8 to 6 to 2 to 4 to 8. And it just keeps repeating over and over again. Oops, no, not that. So using that, we can create a small cycle list that will basically let us know what the last digit of the power of 2 part is. So in this video, how we had so that you will sorry about that, where we had 2 to the a, and we're supposed to find the last digit of this, or the last non-zero digit of this. it'll always be a non-zero digit at the end, apart from, no, it will always be that. So we could just use this cycle of the four numbers to use remainder and easily just check which one it's going to be. So this avoids having to actually calculate the exponent itself. It makes it a lot smaller, less, or more efficient. We don't actually have to worry about calculating anything for this one too. So this is like another optimized version of it too, because we only needed the two part. So rather than doing 2 to the power of a and then checking, we just do that. After that, we calculate a. A is the integer division of n by 5. So, yeah. The a will be what is used recursively or passed recursively, because b, a neat little trick about b is, since it's modulo 5, we could just create a list of the 5 elements that it may be, because it's going to be 0 to 4, right? It's going to go from 0, 1, 2, 3, or 4. Those are the 5 possibilities it can be. And because of that, we could just store those 4, so like single or the last digits or whatever, into a small list, and then we could just easily access it with the index. So the product of all 3 of these last digits will give us the modulo 10, right? The product of all of these will give us the last few numbers, and then the modulo 10 will just give us the last digit that is non-zero. And the recursion happens here. This is the recursive part. It's the only thing that gets passed in for recursion, because a will be cut down, will be divided by 5, so it'll make it a lot smaller, and we pass it in right here. Yeah, I couldn't believe it, how efficient this was compared to the other one. I didn't know how much more efficient it was until I tested it in the Python tutor. So first, let's try out 530 right here, which is the maximum input we can have, as discussed earlier by the constraint. So we're going to submit it. This is the naive approach, the original approach I had, which is just simple factorial, and then after that dividing by 0 until we find it. The problem with this is it has over 1,000 steps, fails to run in Python tutor completely. It fails at 498, I think. Or I don't know which step this would be, but yeah, it's a very, 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 very long number. Yeah, so not optimal at all. Next one. So this is the Geeks for Geeks solution right here at the very bottom. I think this one is yeah, it says it has a worse time complexity of O n log n. But yeah, this is their solution. I wanted to test it out and just see how it worked. I put it in. I have 530 right here. Let's test that one out. This one failed because of the 30 function calls. So the call stack, or the recursion of it, was too long for Python tutor to run it, and it still had 264 steps, which is a lot. So it was just a bunch of function calls happening, and it only really got down to 500, so it still kept going really low. Then we get to my solution. Unfortunately, it's not the most efficient, but it's very close. So at 530, it only has 50 steps, or 56 steps. So let me just skip forward to the last one. It does a couple function calls, and each time it cuts down dramatically. So let's see, the first function call, we start at 530. Second one, we start at 106. Third one, we start at 21. And the last one, we start at 4. After that, we call the function one more time. 4 divided by 5 with integer division will give you 0, and the 0 causes the base case to get triggered, and the base case returns 1, so then we just return from there. So it's a lot quicker than the other two solutions I mentioned prior that failed to even run in Python tutor. It actually runs in very few steps. I was surprised by that. I mean, considering the original approach I had was over 1,000 steps. And this one avoids integer overflow because it's only really dividing or only multiplying small numbers that are usually less than 10 each, or that are less than 10 each. So the maximum number that you can have in here would be 9 times 9 times 9. So that's definitely below the integer overflow. And then there's this one that's the most efficient solution that Geeks for Geeks had. It's right here. So very short, but I don't know. I don't think it's that readable. I'm not sure. I don't know. It does use similar properties though of modulo 10, modulo 2, and division of 5, because that's kind of the big thing that's happening here, where the factorial of 5 is kind of where you start getting the leading zeros from. But yeah, this one is 23 steps total, and it runs iteratively too, I'm pretty sure. Oh no, it's recursive too. So it'll go from 530 to 106 to 24 to 1. Wait, what the? Or to 4? Damn. It does a similar thing to mine then, I think. Oh, mine doesn't. Why does mine have an... Oh no, it doesn't have an 8. Yeah, it goes from 530 to 106 to 21 to 4. So I think this might be the same solution, just a more efficient version of it. I think, because this is basically what I tried coding from what I saw in the video. So probably not the most optimized version, but I mean, it's pretty close at this point. It's 56 steps, and I think this is readable. It's just taking advantage of a couple things, but yeah. It also probably used more function calls in mine because I used this function to separate the logic a little bit for this part. I don't think Geeks for Geeks does any of that. It just does everything in here. So I guess at this point it's like, do you think this is more readable than this? I don't know. But I think both solutions are of log n. I mean, they cut down dramatically, as you can see by the steps. And you can see it just destroy, or like just split up the number by such a large amount, or reduce it down that much. So I'm pretty sure the solution is O of log n time. Would it be... No, it wouldn't be O of n space, because if it was O of n space, that'd be crazy. That would be like more than that many function calls. I think, would it be, I don't know, log base 2 of 530. I don't know if it's close to this. Let's see what this is saying. Log base 2 calculator. 530. 10. I mean, it doesn't do 10 function calls, but yeah, so they're both very efficient. I mean, I'm happy with the solution I was able to come up with. The solution over here, I'm assuming, uses the same principles and properties and formulas and theorems. But I feel like this is more readable. I mean, it separates logic, uses cycles, and explains things throughout the code. So, yeah. That's all.